Hello everyone, thank you for attending. So this work is entitled Evaluating Road Surface Marking Quality Using Synthetic Noise-Based Reconstruction Models. And so this work is done by myself. My name is Boudissa Mehieddine, and I worked under the supervision of Hiroharu Kawanaka and Tetsushi Wakabayashi, these two professors from the Division of Systems Engineering, the Graduate School of Engineering in Mie University in Japan. And so to begin, we're just going to go briefly through the outline. So we're going to go through an introduction and motivation where we will talk about the problem statement, the initial data set we had to address this problem, and our final goal, just to be clear. And then we're going to go through the methodology. We're going to see an overview, and then we're going to see it in two major parts, the data preparation and then training and testing of our models, and then finally we'll see analysis and conclusion. And so for the problem we're trying to address in this work, we're trying to achieve a quality evaluation for road surface markings. And so we have road surface markings are anything you find painted on the road. So it could be lines to determine the lanes, or some special markings like arrows, or it can be sometimes speed limits or something else, or crosswalks or bike lanes, or anything that's useful for traffic management or road safety in general. And so the local government at Mie prefecture in Japan found that they were facing a problem with maintaining these road surface markings, which tend to degrade over time, especially due to some conditions like weather, rainy, especially here in Japan, where you have heavily rainy weather, or just simply too much traffic, or just the road itself degrading. And so we need a framework in which where we can detect and evaluate the quality, so that maintenance can be done with the proper amount of uh, materials and labor force. And so the initial data set, also provided by the local government facilities, uh, sorry, here I said provides two, it's one data set. So the data set consisted of 13,000 high resolution images, plus the quality labels on a scale from 1 to 5. And so, for example, here you have an image, and human beings did their subjective assessment and gave a label to each image from 1 to 5. But what we are trying to achieve in this work, in previous work, we have relied on this labeled dataset, but in here we're trying to go beyond just classifying an image into one of 5 categories, but rather we're trying to achieve assessment on a continuous spectrum. And so basically we're trying to figure out the exact percentage by how much a given surface marking is degraded. And so we took a different approach. So basically our final goal is, given an image from a drive recorder or whatever, something on a car, and then you put it through some pipeline, and then you get uh, a certain percentage that indicates by how much the road surface marking in a certain area is degraded. So the overview of our pipeline is, first we got our RGB images from the dataset shown earlier. We, of course, disregard the labels. We put it through a pre-trained segmentation model, which we trained to extract surface markings in a previous work. And then we obtain our binary masks, and then we introduce synthetic noise to these binary masks, and we train an autoencoder model to reconstruct these binary masks. And then hopefully you'll have a situation where you have a model that reconstructs these images, and then you can compare the original image and the reconstruction, and the difference would be the amount of degradation you have in a certain road marking. And so for the first step, which was where we had where we present our main approach here. So first we did the segmentation as described. You have just an RGB image, and then you put it through a model, and you get the mask indicating the surface marking pixel-wise. And then we introduced noise. And here we decided to go through with creating two separate data sets with two different types of noise, just to have a comparative analysis and to see the effect of different types of noise. And so first we made a data set with random circular noise. And so we just go through the surface marking and we put in random circles with random sizes. And for the second one, we tried to go with something more complex and hoping to achieve something more realistic. And so we did erosion with different filters, followed by Gaussian noise. And so we have seen that Gaussian noise was used in similar applications of basically noising and then trying to recover the noised image, and that's done in diffusion. And so we introduced to each image, we pick a random Gaussian function from this interval we see here. So basically we have the mean from 0.2 to 0.3, and then standard deviation from 0.7 to 0.8. And so for each image, you just pick a random Gaussian from this interval, and then you introduce the noise. And so this gave us our second data set. And so the training and testing process, basically what we hope to achieve is to have a model where you can, so you have a mask, you introduce the noise, and then the autoencoder would try to reconstruct, and then you compare the two, and that would be your loss. So for the model selected, we went with two models, UNet and PSP. And so just as a quick reminder, I'm sure because these two are famous models, and so we're going to go through them just as a brief introduction. UNet is characterized by skip connections. And so these connections which connect each layer in the encoder CNN to the corresponding layer in the decoder CNN. And so by this process hopes to save information and prevent the information loss that happens in the encoding process. And then you have the PSP net, which is characterized by first the dilation operation you see here on the left. So when you have a certain input and then a filter, and so the weights on the filter are spread on the input at different scales, and so not just in the naive way where you just have a filter of 9 values would go on 9 values here, or 9 adjacent values here. And so this helps the model to recover more more features at different scales. And then you're also relying on the pyramid pooling module, which also does pooling at different scales. And so more details on these models can be found in the corresponding papers. And so for our training process, we had an image size of 1600 by 1600. The loss functions selected, we did a weighted combination of dice loss and focal loss, and the reason was because since our task here is that we care so much about what happens on the edges, and so that's what dice loss was for. And then the focal loss, we put it mainly to address the state of class imbalance, because if you look back here at a mask, you can see that most of the pixels here are black and just a minority of pixels is white. And so we have this class imbalance can be addressed by the focal loss. And so during the training, we evaluated the model's performance on the test set. And then we stop the training when the error stops decreasing. So for the results we obtained, these are shown in the tables. You can see this in the paper also. So the best performance went to UNet with a dice score of 80.7 and an accuracy of 96. But then the accuracy doesn't really tell you how well you're doing in terms of recovering the surface markings, but it does indicate how well you're doing in recovering the background, or basically recognizing background as background, which was not the case for the PSP net trained on the erosion Gaussian dataset. And so these numbers would make more sense to see what they actually mean here. And so we, for the circle noise dataset, the UNet model and the PSP model both performed fairly well. On this particular sample, the PSP net managed to do a better recovery, and you can see how both models managed to do the recovery. And then on the erosion and Gaussian datasets, uh, so for this one, the recovery was more challenging. And now for real world samples where for which we don't have ground truth, and so you just bring an actually deteriorated surface marking and you try to recover it. And so this is how we did in terms of, so this is the UNet model. You have here the erosion and Gaussian noise, and here the circle noise data set. And so the edge was for the circle noise data set, and the same happened for the PSP net, but we've seen a decline and a more of a failure in recovering the background. And so just a bunch of comments here. So we have seen the UNet and the PSP net performed better when trained on the circle noise dataset than the erosion and Gaussian noise. We have seen a drop in the quality on real-world data, which suggests the need for improving training methods. And so we need basically to address the domain shift issue. And for the erosion and Gaussian noise versus, or for the erosion and Gaussian noise dataset, we have seen better MIOU and we have seen lower dice score. And so this could indicate that the complexity in noise patterns affects the dice scores, and that the choice of noise patterns impacts autoencoder reconstruction and affects dice and MIOU scores. And so the final remark we thought relevant is that the unit consistently outperformed PSP netting performance. And so now for the issue faced with the domain shift. So we have seen the unit and circle noise trained models performed superiorly in real world examples, and all models showed decreased reconstruction quality when shifting from the synthetic to the real world. And the reasons could be the lack of sufficient representation in our data set, the difference in statistical properties between training and testing data, and basically the validation set, and the real-world surface markings are complex due to factors like, so basically the noise due to real degradation is more complex than our attempted simulation. And finally, in conclusion, in this work we tried to address the problem of quality degradation in road surface markings. We have used pre-existing segmentation model to detect surface markings. We have used UNet and PSP models for comparative analysis to build our evaluation model. And the models showed some kind of satisfactory results on the synthetic data, but not so much on the real world data. And the importance of this field, which we would like to emphasize again, and that this avenue of research improves the road safety and transportation infrastructure. And with this, we come to a closing. Thank you, and open for questions.